In this video, I am going to discuss some of the properties and reactions of thiols, where thiols are sort of the sulfur equivalent of alcohols. And so, as I said, they are analogous to alcohols, and this is because sulfur and oxygen are in the same group on the periodic table. So we can look at this and we see they're in the same column here, and they have the same electron configuration in their valence shell, and so that gives them a lot of the same chemical properties as each other. There are some important differences though. So oxygen has a much higher electronegativity than the sulfur, so about a 0.86 difference in electronegativity. And sulfur is quite a bit larger than the oxygen, so a 28 picometer difference in the atomic radius. And so those are two properties that are different in them that make kind of an important difference in how thiols behave compared to alcohols. So thiols are also oftentimes called mercaptans, so you'll see this kind of terminology used for a lot of thiol-containing compounds. And mercaptan just means it captures mercury because they can form a stable heavy metal derivative with mercury. And so the naming of these is similar to alcohols, except now instead of just the OL, we use THIOL. So for instance, instead of methanol, we now have methane thiol. Sometimes this is called methyl mercaptan. Instead of just one butanol, we have one butane thiol, or you might see it as butane 1 thiol. So here we have 2 butene 1 thiol, and this one here kind of always goes by one of these names here, one of these special names, because this is used quite often, especially in biochemistry. So 2-mercaptoethanol or beta-mercaptoethanol. So this has an alcohol group and a thiol group on it. And these are some thiols that you may hear about just sort of in everyday life. So this dimercaprol here is often called British anti-Lewisite or BAL. And so this was something that can be used against this lewisite, which is a type of poison gas that contains arsenic. And then there is 3-methylbutane 1-thiol. So this is one of the main components in the smell of skunks. So the terrible smell that skunks make. One of the main components of that is 3-methylbutane 1-thiol. And this is actually something with thiols that you hear a lot about, is that they often smell really bad. So obviously this one smells really bad, but so do things like ethane thiol. And so trace amounts of this are put into things like natural gas. That's what actually gives the natural gas smell to natural gas. And that's supposed to be to alarm you that you have maybe a gas leak, because natural gas doesn't actually have a smell. So they put something in it that has a bad smell so that you can actually detect when you might have a gas leak. And if you ever worked in a biochemistry lab too, you know that the beta mercaptoethanol also smells really bad. And so, in general, sulfur containing compounds often have kind of a bad smell to varying degrees. All right, so some physical properties of some of these thiols when we compare them to alcohols. So we start here, so just the hydrogen sulfide and water. So that's just a sulfur with two hydrogens bound to it. We see that this has a much lower melting and boiling point than its oxygen equivalent, which is just water. And so this is also why it has such a poor solubility in water. Well, one of the reasons anyway is because it's not even a liquid at the same temperature range as water, and so it would have to dissolve in water as a gas rather than as a liquid. Then we can look at the methane, thiol, and methanol. So here we have a pretty low melting point here. Then the boiling point is 6 degrees, where we see with methanol it's 65 degrees. Same with ethane, thiol, and ethanol, so 35-degree boiling point versus 79-degree boiling point. And so we can see kind of a general trend here that the thiols are not going to have as strong of intermolecular forces between each other, and so they tend to have, especially boiling point is where you can see this. They have much lower boiling points than their alcohol equivalents. and they are also not nearly as soluble in water as the alcohol versions. So this is the water solubility here, where we see that the methane thiol, which is only 2.4 grams per 100 milliliters, is a lot less soluble than the methanol, which is completely miscible in water. And the same goes for the trend going down here. So 0.68, and this is still miscible. So even when we get to the butane thiol, so this is actually not that far off from this one, because at this point the carbon chain really starts to take over as the main source of intermolecular forces. And so we end up getting similar looking water solubilities here. But then these ones here are completely insoluble, where there's still at least a small amount of solubility for the alcohols here. So that does have to do with these dipole moments. So the methanol has a dipole moment of 2.87, ethanol 1.69. The sulfur containing compounds is 1.52 and 1.57, and so quite a bit less than the oxygen containing equivalents. So the pH of these is also different. So sulfur is larger than oxygen, as we saw above, making it carry the negative charge better than oxygen, and thus thiols are stronger acids than the alcohols. So we can compare the ethanol to the ethane thiol. So the ethanol has a pKa of about 15.9, where the ethane thiol is 10.5. Then with the phenol, it's a pKa of 10, and with the benzene thiol, it's 7.8. So the thiols are stronger acids than the alcohols. And we can see the bond dissociation energies here for these, where for oxygen to hydrogen, it's about 440 kilojoules per mole, and then sulfur to hydrogen is 366 kilojoules per mole. So it's a weaker bond with the sulfur than it is with the oxygen. Then some important reactions of thiols. So thiols can be prepared by the SN2 reactions of hydrosulfide. So like this is sodium hydrosulfide here. So we put this in solution with some kind of unhindered alkyl halide. This can do an SN2 there, it attacks that. This comes off here, and so we end up making a thiol, and then we have this sodium halide here. So thiols themselves are still decent nucleophiles, and this has to do with their large size in particular. So unless we use excess of the sodium hydrosulfide, we can also generate disulfides here. So we could have this thiol then attack yet another one of these unhindered alkyl halides, have this come off, and so we end up making this right here. Unless you have excess of that sodium hydrosulfide, for instance, you're going to get these side reactions as well, since the thiols are fairly decent nucleophiles, at least compared to protonated alcohols anyway. And so some redox of thiols and disulfides here. So the first one we can look at, so we have a disulfide, and then we put two thiols in it, and these are the R primed here, and then we end up with the disulfide of the R primed, and then two of these thiols here. And so it's the beta mercaptoethanol here, where you might use this in, say, a biochemistry lab, where we have like this disulfide bond, such as in a protein, so like a disulfide linkage. We put our beta mercaptoethanol in it, and we can break the disulfide linkage here and generate these thiols here, while making the beta mercaptoethanol into the disulfide here. And the reason that this is used quite often is because having this alcohol group here makes it quite soluble in water, and so that makes it better for this kind of thing, since as we saw above, the thiols are quite a bit less soluble in water than alcohol. So having that alcohol group there makes it soluble in water. So we can also oxidize these thiols with just oxygen here. So we have 4 of these thiols here. We have 1 oxygen. We generate 2 of these disulfide bridges here, and then we also produce a water. And there is also this one, so we bring into thiols, we add this bromine right here along with zinc and hydrochloric acid, and we produce this disulfide here and hydrobromic acid there. And this is also something you'll see a lot in biochemistry. So we have these two cysteine residues, so these are amino acids, and we will form a disulfide bridge right here between those two by doing essentially one of these types of reactions right here. And so these type of linkages occur in proteins fairly often, and so this is something you see a lot in biochemistry. And so another reaction we can do is the generation of sulfonic acids. And so we want to do a vigorous oxidation that can turn thiols into sulfonic acids. And so we can use something like potassium permanganate or nitric acid or hydrogen peroxide or with bleach here, so sodium hypochlorite. And so we can turn this thiol here into this sulfonic acid. So we are oxidizing it and putting these two oxygens onto it here. Well, actually 3 oxygens right there. But anyway, that was everything I wanted to cover in this video. I hope you found this helpful, and I will see you in the next one.